Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to give an introduction to discrete probability. As with most subjects, we begin with a sequence of definitions. What is an experiment? It is a procedure that yields one of a set of possible outcomes. And that is an experiment. We have a name for the set of all possible outcomes for an experiment. The set of all possible outcomes for an experiment is called the sample space. Let me give you an example. Suppose my experiment is to roll one die. The sample space will be the set of all possible outcomes. And on a six-sided die, all possible outcomes are, I can get a 1, 2, 3, 4, 5, or 6. So the sample space would be the set of all possible outcomes. In another experiment, suppose our experiment is a coin toss. The sample space is heads or tails. An event is any subset of the sample space. We're going to consider the case where S is a set of equally probable outcomes for an experiment. Then we're going to let E be a subset of S. So E is an event. What is more, suppose that the cardinality of the sample space is N and the cardinality of the event is K. Then we are going to define the probability of this event to be the number of elements in the event divided by the number of elements in the sample space. It is possible that the event is the empty set, in which case the number of elements is 0, and the probability then for that event would be 0. If you actually perform the experiment, one of those outcomes has to happen. So if nothing happens, then you didn't perform the experiment. The probability is 0. But the biggest that K can get is N. So note that the probability of any event will be a number between 0 and 1. Let me give you an example of an event. On the roll of a die, suppose the event is 2, 4, or 6. In other words, we roll an even number. What's the probability of this event? Well, the probability of that event will be the number of elements, 3, divided by the number of elements in the sample space, 6. So you have a 1 in 2 chance. So you have a 50-50 chance of rolling an even number when you roll one six-sided die. In another example, suppose the experiment is that we roll a pair of dice. And the event that we're interested in is the sum of what we roll is 7. What is the probability of rolling a sum of 7 when you roll a pair of dice? Remember that the sample space might be thought of as rolling a 1 and a 1, a 1 and a 2, a 1 and a 6, a 2 and a 1, 2 and a 2, 2 and a 6, and so on down to 6 and 1, 6 and 2, 6 and 6. So these are all possible elements of the sample space. There are 36 of them. Well, let's list the number of ways that we can roll a 7. We can roll a 1 and a 6. We can roll a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. 1, 2, 3, 4, 5, 6. It follows then that the probability of this event will be 6 divided by 36, or about 1 in 6 times we should roll a dice sum of 7. Let's calculate the probability of winning the Powerball. There are 5 numbers, 1 through 69, and the Powerball, which takes numbers 1 through 26. So we have 5 places to fill, plus the Powerball. There are 69 ways to fill this first slot. We don't allow these numbers to be repeated, so there's only 68 ways to fill this next spot. 67, 66, 65, and there are 26 ways to fill this final spot. So the size of the sample space, the number of different possible ways that the number can be drawn, is 292,201,338. So the probability of winning, there's only one way to win with each draw. So the event of winning has a cardinality of 1, whereas the sample size is 292,201,338. So your odds of winning are 1 in 292,201,338. The complement of an event E is denoted by E bar and defined by E complement is everything in the sample space that is not in E. So in terms of a Venn diagram, if you have some event E, and this is the sample space, then the complement will be everything outside of E. There's a basic theorem of discrete probability that the probability of the complement of some event is equal to 1 minus the probability of the event. So let's prove this. The probability of E complement should be the number of things that are not in E but still remain in S, that's n minus k, divided by the number of things in the sample space, namely n. We can simplify this fraction as n divided by n minus k divided by n. And now you see n divided by n is 1, and k divided by n is the probability of the original event E. And so that's the end of the proof. As an example of an application of the last theorem, suppose that our experiment is to flip a coin 5 times. The event is we have one or more tails appear. One tail, two tails, three tails, up to 5 times, 5 tails. But notice that the complementary event is that we have no tails. This is a much simpler event. The complementary event has only one element, that you flip the coin and get heads 5 times in a row. So notice that the probability of the event E will be 1 minus the probability of the complementary event. Remember, E complement would be E complement complement. The equation holds true regardless of which side you put these terms on. And so you can see then the probability of getting one or more tails, which is more complicated to calculate, will be equal to 1 minus the probability of getting no tails. Well, no tails is easy. How many different possible outcomes are there on flipping a coin 5 times? It's 2 to the power 5. There are 2 to the power 5 elements in the sample space because you have 5 slots to fill and 2 ways to fill each slot. So the sample space has 2 to the power 5. The complementary event has only one element. And so 2 to the power 5 is 32. So the probability is 31 out of 32. A pretty high probability that you'll have at least one tails appear in 5 flips of a coin. In our next example, we're going to suppose that we have 2 events, event 1 and event 2, and we want to find a formula for the probability of event 1 union event 2. Either event 1 occurs or event 2 occurs. As you can see, if we just take the probability of event 1 and add that to the probability of event 2, we've counted these possibilities in the intersection twice. So you have to subtract the probability of event 1 intersect event 2. And that's how you calculate the probability of the union of 2 events. We're assuming here that these are equally probable outcomes, of course. In an example, let's suppose that I'm going to roll a die, one single 6-sided die. Event 1 will be that I roll a 1, 2, or a 3. Event 2 will be that I roll a 1, 3, or a 5, an odd number. What's the probability of either event 1 or event 2? Well, it'll be the probability of event 1 plus the probability of event 2, but that double counts the 1 and the 3, so we have to subtract out the probability of the intersection. The probability of event 1 is 3 out of 6. The probability of event 2 is also 3 out of 6. But we have to subtract the duplicates. And there are 2 in the intersection, so 2 out of 6 is the probability there. So you can see 3 plus 3 is 6 minus 2 is 4. The probability is 4/6, or 2/3. You can see that we're missing 4 and 6 in this discussion, 2 of the possible outcomes. Only 4 are represented in the union.